error propagation. Okay, for all you would-be engineers and physicists out there, or chemists or that sort of thing, you are going to love this, or you will learn to love it. Okay, you're going to be doing this a lot. So let's just talk a little bit about it. Now, suppose you make a measurement, okay, and so we want to measure, I don't know, the length. So we'll say that our length of something is, oh, I don't know, 3 centimeters. But here's the problem. In this measurement, there are issues. We don't know how good our ruler is. We don't know how good our eyeball is. Even if we have a computer or a set of calipers, we can't know how good it is. And so normally they will say, oh, well, it's good to this. And so you'll have an error associated with it. So this is the measurement. Your error might be plus or minus 0.01 centimeters, meaning like, okay, you're good down to 1/10 of a millimeter. Well, that's not bad. But now if you want to do anything with that, for example, you want to, oh, determine the area of something, well, or the area of a rectangle, let's say. Well, then you're going to need a width. Okay, and that width might be 6 centimeters. And we still have the same good error in our measurement of 0.1 or 0.01 centimeters. And so now when you compare these things, wait, you've got a serious issue, because now you've got errors associated with both of these values, and now you have to multiply them. Okay, now our error is going to grow. And this is error propagation. The error continues to gain momentum or to copy itself over every time you do an operation. That's the propagated part. It is kind of moved along the line. Okay, we have to be very careful because we don't really want to get into multivariate calculus, and using these different values certainly can get us there very quickly. And so I'm going to kind of limit it here. And we're going to do an example of a radius. Okay, so if we take a look at this, we are going to give the formula. Well, first of all, here's the idea. The radius of a ball bearing is measured. Okay, so now we're working with radius. So let's go ahead and get rid of our example here. And now we're looking at the radius r of a ball bearing is equal to 0.7 inches. Okay, so now the measurement is good within 1/100th of an inch. And so this is really plus or minus 0.01 inches. Let me put this in. I can't stand writing the word inches out because it makes my teeth itch. And so estimate the propagated error in the volume of the bearing. My pen got screwed up. Okay, estimate the volume or the error in the volume of the ball bearing. Well, now the volume of a ball bearing is equal to, a ball is 4/3 pi r cubed. But remember the error, as we were talking about it, the error associated with that then would be equal to or approximated by, and recall back to our differential discussion, would be approximated by the differential of the volume. But the differential of the volume is equal to the derivative of that, so we call it v prime, times dr. Okay, we're taking the derivative of the volume with respect to r. All right, so that is this right here is our propagated error. Okay, so we can go ahead and work with that. Now that means that if we do that, our dv dr is equal to 4 pi r squared, which implies that dv is equal to 4 pi r squared dr. So the change, or the propagated error on v, is approximately equal to 4 pi r squared dr. Now in this case, it's 4 pi times 0.7 is the measured, the differential, or the error associated with that measurement, is equal to 0.01. And so when we work this out, we get about plus or minus 0.0616 inches. And so even though we were very careful in our measurement, this being our error on of the radius, okay, when we blow it up to the volume and we say, oh, well, we want to make sure that we're in, 1/100th or something like that of an inch of our cubic inches for our volume, we have a problem because we are not. This is our propagated error. Okay, and so what happens is this error gets carried over into the next thing. So we have to be very careful as to how we do this. And this is where engineers come in. They can do these things. And so we want to make sure that when we get to the end, our tolerances are very, very tight. Well, how tight do we have to make the rest of them? Well, now we start looking at, okay, how does one thing affect another? Functions dictate all of that stuff. And now we've got to take the derivative of that and start looking at those functions and how they behave. All of those chain together to start adding more and more and more error in. And effectively, as a quality control engineer, you are looking at, okay, well, how does one thing affect another? And how can I control the error at the beginning of the line so that when I get to the end of the line, I have what I want in the end. All right, there's another way to express this, and this is by far, as far as I've seen, by far the most useful way to express it, and that's the error with respect to the value of the whatever measurement you just made. Okay, now this is called relative error. Okay, and the relative error versus the percent error. And so the relative error would be, in this case, would be 4 pi r squared dr over 4/3 pi r cubed. And 2 r's would cancel out on the top. That goes away. 4's would cancel. 3 would go up top. 5. Okay, so this is going to be 3 dr over r. And when we do that, this is 3 times 0.01 over 0.7, which is going to give us about 0.0429. And this is going to be cubic inches. Okay, that is the relative error. And so this is the absolute error, or the propagated error. And now if you're comparing it back to the other thing, or back to your previous measurement, this thing is called the relative error. Relative error. Then if you change this into a percent, you get the percent error. So you just change it to 4.29%. Poof, there's a percent relative error. And so these things kind of all relate back, and the definition of these tell you how they derived it. So if they're talking about the relative error, well, that means that they're checking it in comparison to the original value of the measurement or the calculation. If they're talking about propagated error, this is the absolute error that's associated with that. More often than not, we are dealing with the relative errors involved.